Thank you. Hi, everyone, and welcome to Microservices, the small print. My name is Mar. That's me taming Pythons. I've been working as a software engineer for almost 10 years now, mostly in startups in Malaga and London. You can find me online by those handles. Chances are, if you're here, you've heard about microservices, probably a lot of good things. But today, I'm going to show you the uglier side of them, the small print. We're going to see a series of examples of real-life scenarios implemented in both a monolith and microservices to compare between the two. We're going to start by implementing a very simple API for a task manager. This would be the specification. We're going to have the concepts of users who can have tasks and can raise invoices for them. We're going to want 3 endpoints exposed over HTTP and coming with JSON. So the traditional way to implement this is just to pick any web framework and pair it with a relational database, and that's it. In here, you can see an example using Django. I defined my models in the ORM, mapped to the database tables, including the relationships between them. And in the views, I declared the roots and then implemented them. Very simple, just fetching the object from the database, serializing as JSON, returning it on the response. How will we do it with microservices? The basic concept is that instead of having one big application, you're going to divide your system into smaller applications, each centered around a domain. So a very simple way to do it would be this, just doing, instead of one big Django, 3 smaller Djangos, each centered around a different domain in my system. Each of the applications is completely standalone and independent. It exposes its own API and has its own database. Of course, there's only one table here on each because it's very simple. But the point is that the databases are disjoint. Notice how there's no relationships between the tables. They are actually implicit. All I hold is IDs to resources that are going to live on different services. Okay, let's spice things a bit now. Let's say that suddenly we get a new requirement, and this is to include the total fee of a task. This is going to be the accumulated amount of the invoices related to the task. In the monolith, we can do this with some clever ORM trick. I'm going to define a dynamic attribute in the model, and because I explicitly declare the relationship between the task and invoices tables, I can get a hold of that relationship and do an aggregate operation. Under the hood, what the ORM is going to do is just turn this into a join statement. I don't even need to touch anything on the view because the new attribute being already exposed on the model means that the serializer is going to be able to pick it up. Unfortunately, on the microservice, I can't do the same thing. Why? Because my data is spread across 2 different databases. If I look at the task model, all that I have available locally is the IDs of the invoices. The data of the invoices is in another castle, in the database of a different microservice. The only way to get a hold of that data is through the HTTP interface of the invoices service. So to get it, I need to do it on the view. After I retrieve the task on the view, I go and iterate over my invoices, and for each of them, I make an HTTP call to the invoices service to get the data. After I have the data, I can then compute the total fee and manually append it to the JSON result before returning. That was not very nice, and not only just because the code was uglier. Notice how we're introducing a lot more network jumps. In the case of the monolith, the only jump that we have is one trip to the local database to get all the data in one go. In the case of the microservices, we have one trip to the local database and then a series of internal HTTP requests, which in turn are going to result in another trip to a different database. Only after all of those are finished, I can return from my original request. It's true that we could simplify this by adding a more clever endpoint in the invoices service to fetch a series of invoices in one go. In this case, I would only need one extra HTTP call instead of several. Still, the moment you have any minimally complicated logic, when you have a microservices architecture, it's not uncommon to have call stacks like this. A service depends on another that depends on yet another one, and then after those get back, you depend on a different service that might even do more calls. And let me remind you, each of these calls is over the network. What this is going to mean is that you better get used to seeing more of this in your application. In very bad cases, even this, and this as well. Welcome to distributed computing. Network communications are slow and frail, and the more of them you have, the latency and probability of failure is going to add up. It's therefore in our best interest to try to minimize the network calls between services. And the only way to achieve this is by being wise when picking the boundaries between your services, so as to minimize the dependencies between them. Okay, this is easier said than done, but how do we do it? It makes sense to look at your data model in order to do a good pick. Imagine this is my data model, the circles being the tables, the arrows being the relationships between them. We can clearly see some clusters of interdependent data, so it would make sense to place my boundaries there, making each of them a microservice. This way, most of the dependent data is going to remain local, and I only have a few cross-domain dependencies. Okay, the bad news is that most systems don't have this beautiful topology. They actually look more like this. Everything is connected, and you have no idea where to draw the cut. If we were to do it by the golden rule of dividing by clusters, we'd have to do it like this, which is hardly microservices anymore. This is a monolith with satellites. Some people still want to force their way into microservices, even if it means ignoring their data model, and they divide wherever they think logically their domains fit. But this is going to be a recipe for disaster. All of these relationships are going to mean cross-domain dependencies, and this is inevitably going to lead to distributed spaghetti. Another problematic area when it comes to network splits is transactions. To see why, we're going to add a transactional operation to our mini API, which is deleting a task. Let's see how to do it in the monolith first. We would go and add the new endpoint. In the implementation, what we're going to do is fetch the task from the database and then enter a transaction context and issue a SQL delete operation. There's more magic though. Remember how we define an explicit relationship between tasks and invoices, including a cascade delete. What this means is that the database is going to do the heavy lifting for me. And when I delete a task, the database is going to automatically delete all of the related invoices in one go, and in a transactional way. You could think that in principle, the implementation in the microservice is going to be the same. Fetch a task and delete it. Unfortunately, if I do this, the only thing that's going to happen is that I'm going to delete the task on my local database. But the invoice data, of course, lives on a different service. So it's going to remain there, untouched, and what's worse, pointing to a task that no longer exists. They're going to be orphaned. If I wanted to clean up, I need to do it manually. So after retrieving the task from the database, but before deleting it, I need to go and make a series of HTTP calls to the invoice service to delete them. But hold on. How many transactions do we have now? Certainly more than one. When I call the invoices service, a new transaction starts. And what this means is that any of those transactions could go wrong. What happens in that case? Imagine I start deleting invoices. The first one goes fine. The second one goes fine. The third one fails. What do I do now? Should I fail and prevent the task from being deleted? Even if I do, I already deleted 2 of the invoices forever. Those changes are committed. Should I just continue deleting the task? Okay, but one of the calls failed. So I have 1 invoice that didn't get deleted and is orphaned. Looks like the CAP theorem is slapping us in the face. On a system that deals with data, you can only have 2 out of these 3. You either have consistent data, immediately available data, or partition data. In the monolith, you don't have a data partition. Therefore, you can have immediately available consistent data. With microservices, however, what you have for sure is the data partition. This means you're going to have to pick either consistency or availability and deal with that manually. For example, imagine that we choose to have strict consistency. What we have to do is somehow maintain distributed transactions. On any error, I'm going to have to fail, plus, undo any changes. So, for example, in here, what I did is, instead of having a series of calls to delete the invoices, I made 1 call to delete them all in one go. If that transaction goes wrong, I fail immediately. Of course, this leads to your system being more frail, because a failure in any of the dependencies is going to propagate upwards in the services call stack. Another popular option for distributed systems is to favor availability with an eventual consistency strategy. What this means is we're not giving up consistency, just not guaranteeing it immediately. Upon any errors, we're going to ignore them and continue, leaving behind inconsistent data. But we're going to try to fix those inconsistencies asynchronously. For example, by retrying failed HTTP calls, or having a background process that is scanning for orphan invoices and deleting them. Even with these mechanisms, consistency is not 100% guaranteed. So I need to be careful when reading to be defensive and protect myself. The system is more resilient than the strict consistency, but at the cost of the data being less robust and my code more complex. Sadly, 20 minutes is not enough to tell you about all the misery that comes with microservices. Basically, if you think of any area of development, it gets worse. But surely there's something microservices must be good at, right? I've heard scalability. Let's remember how to scale a monolith first. The theory is that as you grow, you can start adding replicas of your application and putting them behind a load balancer that will distribute the load equally among them. There's literally no limit as to how many replicas you can have. Here are some examples from the real world. Wikipedia is running in production a PHP monolith, MediaWiki, it's a CMS, on 350 replicas. And only 6 persons take care of all of it. Okay. Reddit is a Python monolith running on 240 replicas in production, also run by a small team. Instagram, Pinterest, and Bitbucket are Django monoliths too. Let's see how we would scale microservices. Basically, it's the same way you would scale N monoliths. The first thing that comes to mind is that even for the basic setup, you are having a lot more machines in production. Even if they can be smaller, this is going to lead to a higher bill in Amazon Web Services at the end of the month. The good news is that we can do some nice things with this. For example, I can scale my systems independently. If I detect that tasks is a bottleneck in my system, I can increase the replicas just for that microservice without touching the rest. Another nice thing is that I can deploy them independently. If I make a change in a monolith, I would have to tear down all my replicas and then bring them back up again. If I have 240 like Reddit does, this is something to be taken into account. If I have a microservice architecture, however, I only need to tear down and recreate the ones of the microservice that I change. The rest don't even need to notice anything happened. Microservices are the chosen way to be in production by the top Silicon Valley companies. In fact, they are the ones that invented the concept in the same place. But if you think about it, their main difference with Reddit or Wikipedia is not so much the amount of traffic, but rather the shape of the company itself. We're talking giants that have thousands of employees, hundreds of teams, and you can imagine how, for them, collaborating over a single code base must be a difficult thing. And in this aspect, having microservices and each team taking care of one of them must be a lot easier for them. It all clicks when you remember Conway's law. Organizations which design systems are constrained to produce designs which are copies of the communication structures of those organizations. So, that was all. We arrived to our conclusions. Microservices are all the hype lately, but before jumping on the bandwagon, please be aware of the small print. Your code complexity is going to increase exponentially. You're going to lose efficiency and robustness due to all of the network calls. Making changes will become more difficult because it will affect a lot of systems instead of just one. And at the small or medium scales, it's going to actually mean higher infrastructure costs than a monolith. They may be justified when you are a really, really big organization because of the easier collaboration on this type of code base. If you have very, very high scalability needs, we mean on the order of hundreds of machines in production, because in this case, it's true that microservices becomes more efficient at scaling than monoliths. And of course, you're going to also need deep pockets to pay for all the infrastructure and development costs. Some situations where people might jump into them, but it's really a bad idea, is, for example, if you're after a better code structure. Many people think that dividing your application into domains is going to lead to better code quality, and they are not wrong. But you don't need to introduce data partitions and network jumps for this. You can divide your application using classes, modules, libraries, and go all domain-driven development. Another scenario is for people who want to future-proof their scaling. So it's like, okay, we're small now, but I believe that someday we will be as big as Facebook, and I want to be ready for when that time comes. Don't do that. Monoliths scale perfectly fine, as we've seen. And if you eventually get as big as Facebook, then you can hire 1,000 engineers and refactor to microservices if you want the little extra bit of efficiency. It's what Facebook did, after all. That was it. Thank you very much for listening, and we have now some minutes for questions. You can also follow up online.